Taylor series. This is from section 10.3 of the book. All right, I'm going to start with a definition of Taylor series. Now, suppose we have a function f and f has derivatives of all orders. So we can find the first derivative, second derivative, third derivative, and so forth. On an interval containing the point A. So assuming we have this, the Taylor series representation of f centered at A is as follows. F, I'm going to write it in green. It's f of A plus f prime at A times x minus A plus f double prime at A over 2 factorial times x minus A squared plus f triple prime at A over 3 factorial times x minus A cubed, and so forth. So this is equivalent to the series k from 0 to infinity of f, the kth derivative of f evaluated at A over k factorial times x minus A to the power of k. Now, if you look at this closely, you will see that this is actually a power series. All right? And so let's just write this down. The Taylor series, well, this is a power series. The Taylor series is a power series with center A and coefficient. The coefficient is ck, and ck is the k factorial evaluated at A, the k derivative of f evaluated at A over k factorial. All right, most of the times, the easiest type of Taylor series is when the center is at 0. So if the center A is equal to 0, the Taylor series is referred to as a Maclaurin series. All right, let's do an example. So, an example. The first example, let's find the Taylor series representation for f of x equals sine of x centered at 0. All right. So why are we calling this a representation? We're calling it a representation because if we can express sine of x as a power series, we're assuming that instead of using the function sine of x, we can just use that power series. And we're going to come back to that. But for now, let's do a quick illustration of how we find the Taylor series of sine x centered at 0. In essence, we're looking for the Maclaurin series. Okay, so we're looking for the Maclaurin series. F of x is equal to sine x. Let's look for the derivatives. F of x, we know f of x is sine x. How about f at 0 is sine 0, which is 0. F prime of x is cosine x. F prime at 0, f prime of x at 0. Oh shoot, how about this? F prime at 0 is cosine 0, which is just 1. And so forth. We have f double prime is negative sine x. F double prime at 0 is equal to 0. And so we have, how about f triple prime? Let me make this a little bit more organized. F triple prime is negative cosine of x. F triple prime at 0 is negative 1. Okay, so the Taylor series is thus 0. Remember what we're doing? We're going with this. I'm going to copy it and show you how it relates. So we have this over here. This is what we're trying to achieve. Okay? So f of a is f of 0. So we're just going to have 0. F of a plus f prime at a times x minus a. So f of 0 is just 0 plus, how about I write it out? We will need f of 0 plus f prime at 0 times x minus 0 plus f double prime at 0 over 2 factorial times x minus 0 squared plus f triple prime over 3 factorial at 0 times x minus 0 and so forth. So that's what we're dealing with. I'm going to erase all this. Okay. So we now have f of 0 is 0. All right. F prime at 0 let's see, f prime at 0 is 1, so we have 1 times x, all right, plus f double prime at 0, we have 0 over 2 factorial, which is 2, times x squared. We can write this as over 1 factorial if we want, times x to the power of 1. And we can write this as 0 factorial if we want, times x to the power of 0. It doesn't matter. Then we have the third derivative. Third derivative is negative 1. So we have minus negative 1 over 3 factorial times x minus 0 to the power of 3, and so forth. And then we keep going. So if we develop that if we follow that pattern, we see that this is going to be 0 over 4 factorial times x to the power of 4 plus 1 over 5 factorial x to the power of 5, and so forth. So there's a pattern we see. But if you look at it, there's a lot of zeros here. So we see that this is gone. This is gone. Essentially, all the even things are gone. All the even, the terms with even powers, they're all gone. So we're going to be left with 1 over 1 factorial times x to the power of 1 minus 1 over 3 factorial times x to the power of 3 plus 1 over 5 factorial times x to the power of 5 minus 1 over 7 factorial times x to the power of 7 plus 1 over 9 factorial x to the power of 9, and so forth. Okay. Now, this is equal to summation k from 0 to infinity 1 over, if you look at, we have even numbers, odd numbers. This is 1, this is 3, this is 5, 7, and so forth. So a way of representing odd numbers is to write it as 2 times k plus 1. When k is 0, you have 1. When k is 2, you have 3. When k is when k is 1, when k is 0, you have 1. When k is 1, 2k plus 1 is 3. When k is 2, 2k plus 1 is 5, and so forth. So this is 2k plus 1 factorial. And then, since the signs are changing, we're going to multiply by negative 1 to the power of k. And then we're going to write this as x to the power of 2k plus 1. All right. Now, our goal is that we want sine x. We want to be able to write sine x as this series. That's the thing. Is sine x equal to this series? Well, that's not the focus of our study. The focus of our study is just to be able to find a Taylor series. So in general, I'm going to say that yes, this means that we can actually express sine x as a series, right? And for this series, for sine x to be equal to this series, we have to make sure that the series converges for all the values that are necessary for sine x to be a function, for all the domain of sine x. So this, what I just explained, is actually a theorem that if the series converges, then the series is equal to the function. We're not going to take that route. We're just going to assume that whenever the series converges, it's equal to the function. And if it converges, if it doesn't converge for all the domain, at the particular interval where it converges, it equals the function. So we now have to show convergence. We have to find the interval of convergence. That's all we need to do. All right, so let's look for interval of convergence. Interval, oh shit. of convergence. If we use the ratio test, we begin with R is the limit as k goes to infinity of ak over ak plus 1. Ak plus 1 over ak. So let's look at our ak plus 1. We're going to look for absolute convergence. So that means let's just not even worry about this part, because if you remember the last time, whenever you take the absolute value, it goes to 1 anyway. Let's just focus on ak plus 1. So that means ak plus 1. So we look at our series. First of all, what's our let's do it one by one. So this is ak plus 1 over ak. Now look at this. This is limit as k goes to infinity. Replace all the k's with k plus 1. So we have 1 over 2 times k plus 1 factorial, right, times x to the power of 2 times k plus 1 That's ak plus 1, and then we're dividing it by ak. So we're going to multiply by the reciprocal of ak, which is 2k plus 1 factorial over x to the power of 2k plus 1. So if you notice, if you look closely, you see that I'm ignoring the x minus 1 to the power of k, because we're just looking for absolute convergence. So we don't need to worry about this. So now let's look at this. This we can rewrite as limit as k goes to infinity of 1 over, that is 2k plus 2, actually 2k plus 3 factorial, all right, x to the power of 2k plus 3, all right, then times 2k plus 1 factorial over x to the power of 2k plus 1. So we can break it down so that we can cancel stuff out. Limit as k goes to infinity, 1 over 2k plus 3 times 2k plus 2 times 2k plus 1 factorial. Then, let me bring it down here. Times x to the power of 2k plus 1 times x to the power of 2. So 2k plus 3 can be written as 2k plus 1, x to the power of 2k plus 1 times x to the power of 2. So now we have 2k plus 1 factorial over x to the power of 2k plus 1. So things are happily going to cancel out. Let's see, this and that. All right, this and this. And then we are left with absolute value of x squared times limit as k goes to infinity of 1 over 2k plus 3 times 2k plus 2. Definitely as k goes to 0, this goes to 0, which is less than 1. So by the ratio test, this converges. So series converges for all x, for x negative infinity to infinity. Okay. All right, so that means we can say that, so we can conclude that the Maclaurin series or the Taylor series for x centered at 0. So let's copy this. So this is our Maclaurin series for sin x. We're going to say how do I want to put this? Okay. I'm going to say they tell us, I'm going to say the Maclaurin series for sin x, or the Maclaurin series representation for sin x converges for x between negative infinity to infinity. Already you're going to have a lot of questions. This is saying that we can write sin x as this, which is good. So remember that this is just the same thing as x to the power of 1 minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the 5th minus ... All right. So what is this saying? This is saying that you can write sin x as the summation of all these terms. For any value of x, we can write sin x as the summation of each of these terms. And now if you look at these terms, this is a polynomial. It's an infinite polynomial, polynomial with infinite number of terms and infinite power. Now you will say, how is that possible? What's the use of that? It's actually useful. It actually turns out that in practice, we can stop somewhere. So instead of going till infinity, we can just go up to maybe 10 or something, right? And in that case, we get a finite number of terms, and we can use it to do what we want to do. Actually, we can just stop here. We can just say that, oh, why not express sin x as just that, right? This is an approximation of sin x. Now, the next question would be, why do we want to express sin x as a polynomial? What's the use of that? You know, the thing is that polynomials are easier to work with. You know, let's say you're writing a computer program, and all you have you want to compute sin x a lot of times, and you find out that your machine doesn't have enough capability for it, capacity. You can use the Taylor series and express everything as a polynomial, express your sin x as a polynomial. And how does that help? Polynomials are just multiplication and addition. That's all. Multiplication, addition, and subtraction. Because this is x cubed is x times x times x, right? So you're just doing only multiplication and addition, which is easier for us to deal with. Okay. So we're going to come back to this when we talk about Taylor polynomials. All right. Let's look at another example. So another example, number 2. How about f of x is equal to e to the x centered at A equals 0. So Maclaurin series again. All right. So we're going to look at f of x. F of x is e to the x. F prime of x is e to the x, and so forth. So this one is nice, actually. F double prime of x is e to the x, etc. So f of 0, is 1. F prime of 0 is 1. F double prime of 0 is 1. So everything is 1. So the Taylor series we are looking at, so remember our Taylor series, our Maclaurin series in this case, is going to be, I'm going to write it in summation form. It's going to be k from 0 to infinity of f, the k derivative of f at 0 over k factorial times x minus 0 to the power of k, right? Because 0 is the center. So this is the same thing as just, let's look at all the terms. So this is when k is 0. So we just have f at the f to the power of 0, or the 0th derivative, is just the function itself. So we just have f of 0 over 0 factorial plus f prime at 0 over 1 factorial plus f double prime at 0. No. I have to multiply by x, right, to the power of 1 plus f double prime at 0 over 2 factorial over x. Let's make it a little cleaner, x minus 0, even though it doesn't make any sense to be put in that, but for clarity, and so forth. So we're just going to have f of 0 is 1. 1 over 0 factorial is 1. F prime of 0 is 1 over 1 factorial times x, okay, plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed, etc. So this is a nice one. Okay, so this will end up just being summation k from 0 to infinity of x to the power of k over k factorial. We've encountered this series before, this power series before, and we know that when we did it, the interval of convergence is actually negative infinity to infinity, okay? And you can show this yourself. So again, what does this mean? This means that the Maclaurin series, representation for e to the x is e to the x is equal to 1 plus x plus 1 over 2x squared plus 1 over 3 factorial x cubed, etc., which is just summation what we wrote before, x to the power of k over k factorial. Okay, and this actually converges if you take the series from k from 0 to infinity. But again, in practice, you only need, if you want to work with this series, you only need maybe that many terms. Okay. All right. So what is this telling us? Let's dig a little bit deeper. So remember that this is a series, a Taylor series, and it's centered at 0. What this is telling us is that if we have e to the power of x, the Taylor series of e to the power of x is a polynomial. What do polynomials look like? So polynomials look like this. They look like the graph looks like something like this, maybe like that, and so forth. Okay. But if you take all the terms, this is a polynomial, assuming you're able to sum all the terms up to x to the power of infinity for some reason, then you're going to get a polynomial that is like this. And it's approximating this function, right? And it's going to go very, very smooth and approximate the function. So that's how we approximate e to the x, a function like e to the x with a polynomial. But in practice, we can sum up to infinity. So let's assume we are just summing from, let's say, okay, I'm going to move this around, put this here, and then let's go like that. So we have e to the x. So this is our e to the x. E to the x. So assuming we're going with just the first two terms, you're going with just the first two terms, right? 1 plus x. This is what you're going to get. You're going to get something like this. Okay? Not a good approximation for our function, e to the x. But look at something. If you consider an interval around the center, say you consider this interval, you will see that actually, it actually gives you a good enough approximation for an interval around, for numbers in this interval. Good enough approximation, not too good. Really, it's bad, but if that's all you got, you can go with it. Now, how about this? How about if we decide to go with, we're going with the first three terms, 1x, 1 over 2x squared. We will end up with something like this. Something like that. Ooh, you see now, we're getting a better approximation. So, in this interval, there's a better approximation. Okay? Now, if you go with more terms, you might get something that looks weirder, but it's giving you a better approximation. And the interval, actually the interval here of approximation for the three terms, it's actually better than the red one. But if you decide to do more, you might end up with, say something like, let's do green. Maybe something like this, like that. Okay. So what do we see? So this is just this is 1 plus x plus 1 over 2x squared, and this green one is 1 plus x plus 1 over 2x squared plus 1 over 6, 3 factorial is 6x cubed, etc. Okay? So you see that the interval that it's giving you good approximation is now increasing. So the point is that the number of terms you take, you take in the series, the better approximation you get, and the wider wider the interval, the you can get the good approximation on. Okay, so we call these Taylor polynomials. Okay, so our Taylor polynomials for e to the x, the first one, maybe p0 would just be 1. Okay, p0 of x, your p1 of x is just the first two terms, the polynomial of 1 degree, 1 plus x. The p2 of x is just going to be 1 plus x plus 1 over 2 x squared. And p3 of x would be 1 plus x plus 1 over 2 x squared plus 1 over 6 x cubed. All right, and the higher the degree of the polynomial, the better approximation you can use this polynomial to approximate e to the x. Again, polynomials are useful. Another reason why polynomials are useful that I forgot to mention is that we can always find the derivative of a polynomial. Always. It's easy. Use the power rule. You can always find the integral of a polynomial. Use the power rule, right? Polynomials are easier to work with. So that's why, in general, if you can represent a function as a polynomial, it's a good thing. You do it, and you can work more with that function. Now, we've looked at the integral, we've looked at the Taylor series for a bunch of functions, okay? For two functions, actually. I want to summarize, or I want to give you a table of Taylor series for many more functions, right? That you can actually find yourself. I want you to try each of them, find a Taylor series, the Maclaurin series for each of them. A table of remember, the Maclaurin series is Taylor series centered at 0. Table of Maclaurin. So the first one we did was sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial plus x to the 7th over 7 factorial. No. Minus x to the 7th over 7 factorial. Alright, so this is the summation. We know that this is summation k from 0 to infinity of negative 1 to the power of k over 2k plus 1 factorial x to the power of 2k plus 1. And this is valid for x from negative infinity to infinity. Okay. Now, if you follow just the way, if you follow what we did with sine x, you can obtain this for cosine s. You can obtain the Taylor series, the Maclaurin series, Taylor series centered at 0 for cosine x over 4 factorial minus x to the power of 6 over 6 factorial, and so forth. So this is another way to show you that the sine function is an odd function, and the cosine function is an even function, because you can see that all the powers in the sine function, in the sine series, are odd powers, while those of the cosine series are even powers. All right. Now, we also did e to the power of x. I really love e to the power of x, the Taylor series. In general, I love this function. Its derivative is itself, its integral is itself, and so forth. Remember, we got 1 plus x squared plus x to the power of 3 over 3 factorial, x squared over 2 factorial, and then we kept going, and we can represent this as k from 0 to infinity x to the power of k over k factorial, and this is valid for x between negative infinity and infinity. Okay, all right. Number 4, 1 over 1 minus x. This is a good one. 1 plus x squared. I actually prefer this one to e to the x. X cubed. If you do this correctly, you will see that this will remind you of a series that we studied extensively, the geometric series, where r is your x and your a is just 1. So this is, remember, if you put 1 here, so that would be your a for the geometric series, and this x would be your r. Okay, so this, you don't even need to worry too much about the radius of convergence, because this is a geometric series. Its radius of convergence only works when x, when x is, the absolute value of x is less than 1. Okay, now we can also look at something like this: 1 plus x. Okay, 1 minus x plus x squared. Okay, minus x cubed, and so forth. And you can actually obtain this from number 4. Remember, look at this. This is just replacing, this can be written as 1 over 1 minus negative x. So if you just replace all the x's with negative x in number 4, you get the series for 1 over 1 plus x, and this is summation k from 0 to infinity of negative 1 to the power of k, x to the power of k, and this is for absolute value of x less than 1. So I would encourage you to remember this series expansion for Maclaurin series expansion for these functions. These are the main ones that almost everybody that studied Calc 2 know. Sine x, cosine x, e to the x, 1 over 1 minus x, and then 1 over 1 plus x. In the next video or in class, we're going to learn how to use these series, the 5 of them, to come up with the Maclaurin series for other functions, other related functions. All right, I'll see you in class.